Much, Sammy. So yes, I have the joy of being a little bit like Keith and a little bit like Tim in that I'm an experimentalist who has just happened to drift into computational work from time to time. So what I'm going to talk to you today is largely about the sort of work on machine learning that I've been doing fairly recently. And I'll give you some of the results, and it may be a bit low level, but hopefully it'll be interesting to some of you and some interesting things across the board. So first of all, I wanted to just start off with a question. This is, what is the link between these various things? So just think about it in your mind as we're going through, try and work out what might join all these things together. So applications such as solar cells, capacitors, ultrasound machines, so that's going somewhere completely different again, fuel cells, so one other thing again, and actually even some types of computer RAM, not all of them, just some, and just to really add a curveball in, 38% of the Earth. So there's one thing that actually links all of these together. If you want to throw it in the chat, you can. I can't actually see the chat at the moment, but I'll put you out your misery. It's the atomic structure. So all of these things arise from the same atomic structure, and that is actually this thing here, which is called perovskite. So as Sammy said, I'm an inorganic chemist. I'm interested in solid state materials, lots of metals and oxygen predominantly. And so all of these applications are built on the perovskite structure, which is incredibly flexible, has lots of interesting properties. And so this leads on to what I think is a very fundamental tenet of chemistry and much of physics, and that is that atomic structure dictates your physical properties. So another way of viewing that is that if you know where your atoms are, you could in theory predict everything that's going to happen in that material. So there's some examples which are fairly obvious, some of them quite interesting. So for instance, diamond versus graphite, they are both carbon, but diamond is obviously very hard, graphite is very soft. That arises purely because of the change in the atomic coordination. Other examples include things like cisplatin and transplatin. So cisplatin is a very, very good anti-cancer drug. Transplatin, where you're just swapping the positions of your ammonia and your fluoro groups, that's completely useless as an anti-cancer drug. So just that small change in structure has a big effect on its biology, or the effect of the biomedicine. Other examples include things like the carbone molecule. So here we've got the stereogenic center. And if you have the R version, that smells like spearmint. If you have the S version, that smells like caraway. But moving back towards the inorganic materials again, a nice example is vanadium dioxide. So this is an interesting material that's actually used in some smart windows, like you get on Dreamliner aircraft when you used to be able to fly. And so these smart windows have VO2, which changes its state depending on temperature. So hopefully you can just about make out these pictures. At high temperature, all of your vanadiums in this rutile-like structure are the same distance away from one another. And this is a metallic structure. And so actually it absorbs quite a lot of light. So that's why it appears quite dark in color. As you cool it down below about 30 degrees Celsius, it undergoes a phase transition where your vanadiums actually pair up. So hopefully you can see you've got two vanadiums joined by a short green bond here, and then a long yellowy orange bond between two. So it goes short, long, short, long, short, long along these chains. And that's an insulating material. And so actually that doesn't absorb light at all. So it is more or less colorless. And so the reason this works in smart windows is you can put it on the outside of a building. When it's hot weather, it's dark, so it stops extra sunlight coming in. When it's cool, it's nice and clear, so then lots of sun can come in and warm your rooms up. So it's quite useful in being commercialized. So having said that, the atomic structure dictates the physical properties, we can think a bit more abstractly about how we can describe this. So crystals in particular, which is what I'm interested in, have obviously both a crystal structure and some sort of composition. And I would argue that if you're similar in both of these, you're going to have the same properties. So as a very simple example, we go back to diamond again. Here on this structure composition axis, diamond is there. We can also consider something like cubic boron nitride. So that has the diamond-like structure. Boron and nitrogen are next to carbon on the periodic table on either side. So compositionally, it's very similar to diamond. So you would expect these two materials to be quite similar in terms of their properties. Conversely, if you think of graphite again, it's got the same composition as diamond, but a very, very different structure. So this is somewhere way out there. And we can think of other examples as well. So rather than changing the structure and keeping the composition same, what happens if we keep the structure but change the composition? So that would give us something like alpha tin, which could be up here somewhere. And if you go in the literature and look at the properties of these things, as you might expect, cubic boron nitride and diamond are both what's known as super hard materials. So these are both incredibly hard, and they occur in this same sort of space. And so this idea of being in the same place in the structure composition and having the same properties seems to fit. The problem comes in if you then look at the other two. So graphite versus alpha tin, they're actually both semi-metallic. And so on this simple two-dimensional plot, they're a long, long way apart from each other. You wouldn't expect them to both be semi-metallic. So the real challenge with this structure composition space is how can we define our similarity? And in this case, we can make it quite simple, really. We just add a third axis. And if you add a third axis and stretch them apart, now you can still have your cubic boron nitride and diamond close together, your graphite and your alpha tin become close together, and all still works out. So the whole idea of this is that if you make this multi-dimensional space complex enough, eventually everything will drop into the right place. So materials that have the same properties will be in the same place, materials that have different properties will be in different places. The real challenge is how many dimensions do you need to do this, and how do you define the dimensions in the first place? And so this is where machine learning comes in very handy. And so just for the sake of this talk, I'm going to focus on structure, but you can do the same sort of ideas. We've done some work on this, looking at composition as well, but just for the sake of time, I'll focus on the structure aspect. So thinking about crystals then, in terms of machine learning, we want some way of describing this multi-dimensional space. The big problem that we have is that crystals are infinite. So that would immediately give you an infinite dimensional space if you just took the atomic positions in your crystal. And that's a nonsense. It just doesn't work. So many of you, I imagine, will have done some crystallography. The common way of doing this is that you take a unit cell. So you find the smallest repeat unit of your crystal. In this case, we're looking at something like rock salt. And you just use that and its translational properties as the sort of unique identification of your crystal. And this is very convenient and very well defined. So crystallographers have been doing this for many years. We have a well formatted way of discussing these in terms of the shape of our box, so the shape of our lattice parameters, the coordinates of each atom within the box, and also symmetry. And even better from the point of view of machine learning, there is a standardized format for delivering this information. So this is the crystallographic information format, CIF. And that's really nice. It's well defined, everything has its place, everything is logical. But, and there's always a but, the big problem is that crystal structures are not unique. So if you imagine a simple two-dimensional array of repeating atoms here, you could define a unit cell that starts on your orange spheres and looks like that. That's great. That you could then feed into a CIF file. In theory, you could put it into a machine learning program. Unfortunately, you could also have a unit cell that looks like this. And it still defines the structure exactly the same. It contains all of the important structural information, but it's not the same representation. And so it comes back to something that Keith was saying earlier about this idea of you need to generate some sort of features in order to map these things into your structure composition diagram. If you can have the same material with two different descriptions, then that's a real problem. And I can keep doing this forever. I could draw an infinite number of unit cells that are all completely equivalent. So there are ways around this. And this comes up with the idea of materials descriptors. And so this taking your crystal structure in some way representing it, so handcrafting these features, as Keith talked about, which you can then feed into smaller machine learning pipelines. And there's lots of these about. The important things are that they have to be invariant. So if you rotate your structure, your descriptor can't change. If you swap your atoms over, so if you have an oxygen 1 and an oxygen 2, if you label them the other way around, your descriptor has to remain the same. And ideally, these also need to be invariant to the system size. So if you have an extra atom in your unit cell, it can't break. And so this is where a lot of them fall down. So a really common one is the Coulomb matrix, where you're looking at the distances between atoms and you just ended up with a pairwise distance matrix. This is fine as long as you're always looking at the same number of atoms. If you try and add in an extra one, then suddenly your Coulomb matrix gets bigger. And machine learning on the whole doesn't like your inputs to be different sizes. Another approach that's quite common is that you just throw the kitchen sink at it. So you take all of the properties that are known about your atoms and you try and just put them all in together. And that works quite well, but it's obviously quite time consuming. It also relies on you picking out the features in the first place. And so there's a number of ways around this. The ones that Keith talked about earlier, these graph convolutional networks, they're really good in that you don't have to define the features. You can just put the structure in a well-defined form. One problem that I see with that is that you have to decide which atoms are bonded to which other atoms. And that's not necessarily trivial for some of the things. And it also does limit you in terms of which machine learning architectures you can use. Graphs cannot be completely transferable between different models. So I reached this from a sort of very early point of saying, well, somebody must have come up with a good descriptor that describes everything. And one of the simplest is perhaps interatomic distances. So here you're just looking at what are the pairwise distances within your structure. So as a simple example, here I've taken perovskite again, starting at this titanium atom here in blue, you can draw a shell out to increasing distances. So the first thing that you come to as you radiate out from this titanium are these oxygen atoms here. If you look a little bit further along, you're looking at strontium in green. This is actually slightly out of the plane, which is why the distance doesn't quite line up. And then you can keep going. So then if you go a bit further, you reach the next set of titanium atoms, then the next set of oxygens, and so on and so on. And you build up this histogram of distances. And that's fine, but it has a real problem that it's quite lossy. You're compressing what is a three-dimensional structure down into effectively one dimension. And particularly at long length scales, everything starts to overlap and it becomes a bit of a mess. And if you've got a very complex structure where you've got lots of unique atoms in your unit cell, you can't really pull much of that information out. So here is the same histogram now plotted with a bit of Gaussian broadening to add some size to the atoms. And that's plotted up to 10 angstroms. You can see it very rapidly becomes quite complicated. So our idea was to take that RDF approach and instead group it together. So try and keep the same information, but actually get better information from it. So it's a very simple idea in a sense. You just rank the distances for each unique atom. So just to walk you through an example, you first look at your structure, work out how many unique atoms you've got. So in this case, I've just highlighted some spread out translationally just to simplify how I display it. And for each of them, you first find what is their shortest distance. So you just look around and find the nearest atom of whatever type, and then plot that into a histogram. So here, it's a bit smaller on my screen, hopefully you can see it. These are colored by which atoms are bonding. So this first peak comes from your titanium bonding to your oxygen, or vice versa, oxygen bonding to titanium. This second peak here is your strontium oxygen peak. And then you carry on. So you look at the next neighbor for each atom. So the second neighbor, that becomes your second shell in this grid representation. And you can keep on. So then look at the third neighbor. And what you'll have seen here is that actually these oxygens are two coordinate formally in a perovskite. So as soon as you've got past shell 2, you're onto a second coordination shell for your oxygen. So this peak seems to jump around a bit. And you can keep on higher and higher shells as far as you like. And you get a unique representation like this that actually you retain all of the information of the RDF. So if you sum all of these up, you extract the same RDF you had before, but each shell retains some sort of information about the local character around the atoms. And so this is really nice as a descriptor. It's invariant to rotations. As we said, it's invariant to translations. It's completely invariant to swapping atom labels. It doesn't have any atomic labeling in there at all. And one real benefit of it is it's quite fast. So there are lots of programs for computing atomic distances that work very, very quickly. And so you can calculate these things without much difficulty, which is always good if you're looking at many thousands of structures. And a final point is that actually it's, I won't say unique, but it is relatively unique. So for a given structure, it has one grid representation, but one grid representation maps back to very few different structures. And basically, it's the same problem as a Patterson map in crystallography. You have a small family of structures that will give the same grid. So having then generated these representations, the question is, how can we use them to define similarity? What is their distance in this structure composition space? And so two examples here is just the cubic perovskite again, and also a tetragonal perovskite, which stretched it along the c-axis. And they're subtly different in their grid representation. There's some sort of shoulders on these peaks. And so the approach that we came up with was just to basically do pairwise comparisons. So you compute a distance between the first shells, the second shells, and so on and so on. And then overall, our dissimilarity is just the mean of these. And that's great. The problem is then, how do you define this distance between these two shells? So just to walk through a simple example, if you imagine three distributions, we've got A, B, and C. If you use something like Euclidean distance, which is something that is normally used in machine learning, there's a problem with Euclidean distance that it's not very good at comparing probability distributions. So in this case, hopefully from a sort of intuition point of view, A and C are actually closer together than A and B, if you're just thinking about bond distances. But Euclidean distance will give it the other way around. Euclidean distance, because you have a peak in this first bin in both cases, it says that the distance between A and B is less than the distance between A and C. So we very quickly scrap Euclidean distance as a metric for this. And instead we move to Earth movers distance. So this, I won't go through the maths of it, but fundamentally you're looking at how much effort is required to transform one distribution into another. And so all of this work is done using Earth moving distance, which gives the sort of chemically sensible way around. So just to walk you through a couple of examples then. And the first one is a Ruddleston-Popper series. So this is an intergrowth structure between what is effectively rock salt and perovskite, with different amounts of rock salt or perovskite layers, depending on this integer n. And so it's an infinite series. We only looked at a few of them and computed the pairwise EMD between them. And I just want you to focus in on this bottom row here, highlighted in green. So using our grid representation and Earth mover distance, you can see that obviously a structure with itself has an Earth mover distance of 0, but as you move along this Ruddleston-Popper series, your Earth mover distance is getting larger. So the infinite one is most dissimilar to n equals 0. Conversely, if you just look at the summed RDF, or the basic RDF, it actually predicts that the infinite one is closer to n equals 0 than to n equals 2, which chemically is nonsense. So that's a tick for grid in terms of making chemical sense. The other thing is lattice expansion. So if you take a crystal structure and blow it up a little bit, your bond distances are all going to get bigger, but depending on which way they're pointing in the crystal structure, they expand at a different rate. And so this is a problem for Euclidean distance, but actually also for the summed RDF, you can get distances jumping between bins at different rates. So we've simulated a cubic perovskite at different volumes, calculated the pairwise Earth mover distance again, and you can see that grid gives a nice smooth behavior as you'd expect. So a material that is closer in lattice parameter gives a smaller EMD, whereas your original RDF distribution gives all these discontinuous jumps, which doesn't make any sense chemically. So the grid works really well in terms of quantifying this similarity. So then as a sort of final example, I just wanted to say how we can use it to actually do something useful. So in this case, we turn to a nice benchmark, which is trying to predict bulk modulus from structure. So you take a structure, you can try and predict how hard it is. We've used a number of different machine learning approaches. The simplest one that actually works really well is a k-nearest neighbors approach, where you basically look at a point, find the point in the structure composition space that is nearest, and say that it's got the same bulk modulus. And so here, bottom left, we've got a training curve of how this changes as you add more data into this KNN and also the KRR approach. And we can see that we can get down to about 32 gigapascals mean absolute error. with just the structure. If we add in composition information as well, we can get down to about 20 GPa. The mean absolute error of the state of the art, which is based on a graph neural network, is actually about 10 GPa. But actually, because this data is skewed, if you use the median error, which is arguably a better measure, we reach a 9 GPa median error. So that's as good, if not better, than the state of the art. And just to show you how these are comparing, there's no systematic errors here. It's almost random depending on where the data are. And the real benefit of ours is that KNN is a very simple model compared to a graph model, which requires quite a lot of data and careful training. And just as a last thing, so Keith helpfully showed some TS&E plots earlier and described what they were showing. This is the same data plotted in each case, colored by a different property. So our bulk modulus is this first column here, and you can see that actually the grid clusters bulk modulus quite well. Composition adds a little bit more. If you combine them together, you get a really good distribution of high bulk modulus versus low bulk modulus properties. But if you color the same TS&E plots with different properties, you can see that this actually translates quite well between different physical properties. So things like shear modulus, formation energy, which Keith talked about earlier, we can predict that, not as good as the state of the art, but reasonably well. And then finally, band gap as well. You can actually get quite a good band gap prediction just from looking at this structural representation. So just in conclusion, then I want to sort of say that grid is this way that we've introduced of trying to rationalize this structure composition space. And it seems to do quite a good job and is fairly simple and fast, and actually works a lot like a chemist, whereas some of the other machine learning approaches and other descriptors are not quite so intuitive. And it matches bulk modulus. Actually, the important thing here is that it generalizes to other properties. So that's something we're exploring a bit more. So just to finish with some acknowledgements, Ruichi Zhang was a postdoc who worked on this and did a lot of the hard work, and also Sohan Seth here at Edinburgh, who's a collaborator on this, and a range of postgraduate and master's students who've done a lot of work on this over the past couple of years. And finally, these people for funding and you for listening. Thank you very much.